All right, these are the answers to the free response questions. The first one, we're given a nuclear symbol and asked to compute the charge, the proton count, the neutron and electron count. We see we have indium, so we can consult our periodic table and find out indium has 49 protons. The fact that the 3 plus after the In symbol tells us that the charge is 3 plus. And that means that I've got 3 fewer electrons than I do protons. So my electron count would be 46. My neutron count comes from the difference between the mass, 115, and the proton count, 49. And the difference between those two numbers is 66. On the second line, I can do the same thought process for phosphorus 32 with a 3 minus charge, and I get these numbers. The third line, we kind of go the opposite direction. We know that we've got 35 protons and 36 electrons, so I need to find the element who has 35 protons. Well, that would be bromine, and I've got a -1 charge because I've got 1 extra electron. And I'm looking for the atomic mass. That would be the sum of the protons and the neutrons, or 80. And when I do that for the last row, I see that I get barium 137, 2 plus. All right, for number 2 and number 3, these are sort of opposites. On number 2, given the name, I need to come up with the formula. All right, our first one, cobalt-2 carbonate. That's going to have the formula CoCO3, and that will be an ionic compound. Our second one, barium chlorate, BaClO3, 2. Barium has a charge of +2, chlorate -1. Again, an ionic compound. The third one, dinitrogen trioxide. The fact that we're using the di and tri prefixes tells us that this is not ionic, it's covalent, and this would have our formula N2O3. Ammonium phosphate. Ammonium has a charge of +1, phosphate -3, so I need 3 ammoniums. An ionic compound, sulfur tetrafluoride. Again, it's going to be covalent, so our formula will be SF4. All right, part 3, or question 3, kind of asks us to go the other way. Given the formula, what is the name of this compound, and is it ionic or covalent? Well, Cl2O7 would be dichlorine heptaoxide. Hepta is the prefix for 7 of something. This would be covalent because I don't have any metals. The second one would be magnesium nitrate, again ionic. The third one, potassium sulfide, ionic. The fourth one, I don't have any metals, so this would be covalent. But here I would have phosphorus pentabromide. And then the last one, this will be copper 2 acetate. I use the Roman numeral 2 because copper has 2 possible oxidation states, +1 and +2. Acetate is a charge of -1, and I have 2 of them. Therefore, this must be copper 2 acetate. Problem 4. A chemist needs to determine the empirical formula of an unknown compound which contains carbon, hydrogen, nitrogen, and oxygen. And they give us the sample weight and then the various masses of some of the reactants. A, determine the mass in grams of carbon. All right, everything has got 5 sig figs in it, so we're going to keep that amount in our answers. I've got 6.8618 grams of carbon dioxide. That's given to us in the problem statement. But only part of the mass of carbon dioxide is carbon. So I can multiply by this ratio, which would be the atomic mass of carbon, 12.01, divided by the molar mass of carbon dioxide, 44.01. And when I do that math and keep 5 sig figs, I get 1.8725 grams of carbon. Now, part B asks us to determine the mass in grams of hydrogen in this compound. Well, it's a similar kind of a problem. The problem statement says 1.7557 grams of water. Here in water, I've got 2.016 grams of hydrogen for every 18.016 grams of water. And when I do that math and keep 5 sig figs, I get 0.19646 grams of hydrogen. Part C, when the compound is analyzed for nitrogen content only, the mass percent of nitrogen is found to be 14.14%. Determine the mass in grams of nitrogen in this sample. Well, this part has 4 sig figs in it, so we'll keep that amount in our answers. And I've got 3.8625 grams in the overall sample times 14.14 divided by 100 to convert it back to a decimal. And I get 0.5462 grams of nitrogen. Now, part D says determine the mass in grams of oxygen. Well, I've got the mass of nitrogen, carbon, and hydrogen. So for oxygen, it's just by difference or by subtraction. So I just do a subtraction problem and I get 1.2473 grams of oxygen. Part E says determine the empirical formula of the compound. To determine the empirical formula, I take each of the masses and I divide by its respective atomic mass. So when I do all that math, I can convert the grams of each of the compounds or each of the elements in the compound into moles. And now you see the number of moles. But I want to sort of normalize this because it's hard to look at these numbers and try to make sense out of what I've got. So if I divide by the smallest of the numbers, whichever one that is, one of those numbers will be a 1. And in fact, we can see that would be nitrogen. But if I divide them all by the same number, 0.03899, I get these 4 numbers, 4, 5, 1, and 2. And that must make our empirical formula C4H5NO2. Part F, in another experiment, 8.65 grams of this compound contained 1.75 times 10 to the 22nd molecules. Calculate the molar mass. Well, if I've got 8.65 grams for every 1.75 times 10 to the 22nd molecules, I can multiply that by Avogadro's number. And if I do the unit conversion properly, the molecules cancel and all I'm left with is grams divided by moles, and my number comes out to be 298 grams per mole. All right, problem 5. Liquid pentanol. Pentanol is an alcohol, a 5-carbon organic alcohol. It undergoes complete combustion in the presence of oxygen gas, according to this reaction. You should remember that any combustion reaction is a hydrocarbon reacting with oxygen to form carbon dioxide and water. A quick review will see that this is a balanced reaction. Not all the reactions you get in AP Chem will be balanced, but this one is. Part A, calculate the following quantities, moles of pentanol. All right. I am given 7.35 milliliters of pentanol. So I've got to convert that to grams of pentanol. I do that with the density by multiplying by the density. You can see milliliters cancels out. And then I've got to divide by the molar mass. That number is not given to us, but it's easy to calculate if we have a periodic table, which you always will. So when we put all those numbers together, I get 0.0679 moles of pentanol. Part 2, we need to get the moles of oxygen gas. Well, we're given 16 liters, and we're given the density of oxygen, 0.922 grams of oxygen per liter of oxygen. So liters cancel out. And now I have grams of oxygen, and I can divide by the molar mass, but it's oxygen gas, which would be O2, not monoatomic oxygen, which would be 16. So 0.922 divided by 32 times the 16 liters originally that I have is 0.461 moles of oxygen. Part B, identify the limiting reactant in this experiment. Limiting reactant, also known as limiting reagent, and justify my answer. All right, from the balanced reaction, stoichiometry requires our oxygen to pentanol ratio be 15 to 2. We get that by looking at the stoichiometric coefficients. So 0.0679 moles of pentanol times 15 moles of oxygen for every 2 moles of pentanol means I need 0.50925 moles of oxygen required. I don't have that much. We only had 0.461 from the previous part of this problem. So that must mean that oxygen is the LR, or the limiting reagent. We need to calculate the theoretical yield of carbon dioxide in grams that could be produced from this experiment. When we have a question like this, we do all of our yield calculations on the basis of the limiting reactant, which in our case is 0.461 moles of oxygen. So 0.461 moles of oxygen times 10 moles of carbon dioxide for every 15 moles of oxygen, again, from the balanced reaction, times 44 grams of carbon dioxide for every mole of carbon dioxide gives me 13.5 grams of carbon dioxide. Okay, if the mass of carbon dioxide recovered from this experiment is only 11, we need to calculate the percent yield. Well, the percent yield is going to be the actual amount, which is 11 grams, divided by what we should have got when we did our theoretical calculation, which was 13.5 grams. So when we divide those numbers, we get 0.813 or 81.3%. That's the end of the free response problems for the practice test. If you have questions about these problems, you can contact me over the summer by my email address, or you can wait until school starts and you can contact Dr. Rowe directly, or you can wait until school starts and contact me directly. But going forward, you will be working with Dr. Rowe. I'm happy to entertain whatever questions you've got over the course of the summer. Please make sure that you understand how to do these problems through and through, forwards and backwards. These must make complete sense to you. If they do not, you've got to speak up. This course will go too quickly for you to hold your questions. Good luck, and we will talk to you in August.